So in this session we are going to discuss about Fourier series for the power electronics. Before going into the topic, why we are reading the Fourier series here? So because a Fourier series is a tool which analyzes the voltage and current waveforms of the rectifiers as well as the inverters. So and here the Fourier series is a tool to analyze the total harmonic distortion also. If you spend for the 30 minutes of this video, so you can answer or you can write the Fourier series expression of any waveform which you will come across power electronics. That is the current and voltage waveforms of the rectifiers as well as the inverters here. So and one more thing is, so here by memorizing the three waveforms or by doing the Fourier series for the three waveforms, you can answer and you can write the Fourier series expression for any waveform in the power electronics. So here I am going to give you the Fourier series expression for all the waveforms which you will come across the power electronics, So at this stage, it is most important to get all these concepts at one place, and you spend 30 minutes here. So and by completing this topic, so you can answer some of the previous gate questions also. So here, let me start the lecture here. So let me find the first waveform, which is square waveform here. Let me find the Fourier series here. So we know that the Fourier series expression is, so the basic Fourier series expression is f of omega t. So f of omega t equal to, so which is the combination of Fourier coefficients. We know that is a naught plus sigma an into cos n omega t. So n into 1 to infinity. So an cos n omega t plus sigma n equal to 1 3 infinity, so 1 to infinity bn into sine n omega t. So bn into sine omega t. So let me find the Fourier series expression for this. So if you can remember the Fourier series expression, so this is the one of the waveform. I said three waveforms, so this is the one of the waveform in that. So now let me find the Fourier series expression for this. So first we need to find whether it is an odd symmetry or not. So because if you observe this waveform, so this is symmetry over the origin. This waveform is symmetry over the origin. So this waveform is symmetry over the origin. So it is the odd symmetry. So it is the odd waveform. So right, it contains odd symmetry. Now we need to verify the quarter wave symmetry condition is there not. So what is quarter wave symmetry? So quarter wave symmetry is nothing but, so it should satisfy the condition of x of theta p minus theta equal to, so x of theta p minus theta equal to x of theta p plus theta. So x of theta p plus theta. So what is theta p here? So a theta p is the angle at which the maximum value occurs. So here we know that at 90 degrees and 270 degrees the maximum value will occur. So that it will be the x of 90 minus theta equal to x of 90 plus theta. X of 90 plus theta. Similarly, so one more peak value is x of 270 minus theta equal to x of 270 plus theta. So let me verify this one. So how we can verify this one? So 90 minus theta, here if I go left side to the 90 degrees, it is 90 minus theta. If I go right side to the 90 degrees, it will be the 90 plus theta. So here if you observe here, so in both the sides the waveform nature is and waveform shape is same. So that again let me find at 270 degrees also. If it is satisfied for the 270 degrees, we can say that it contains quarter wave symmetry. It contains quarter wave symmetry. So if you observe for 270 minus theta equal to 270 plus theta also, so it contains quarter wave symmetry. So why we have found that with whether it is odd symmetry or quarter wave symmetry here? So because if it is an odd function, so the BAN value is 0 and BN value we need to find. So BN is not equal to 0. So in this expression we can make the AN is 0, so that it is not possible to find the AN value. So it is not required to find the AN value. So here, so BN we need to find. And one more thing we have determined whether it has the quarter wave symmetry or not. So why we have determined the quarter wave symmetry? Because if waveform contains quarter wave symmetry, the even harmonics are 0. If contains quarter wave symmetry, the even harmonics are 0. So even harmonics are negligible. Even harmonics are negligible. Now let me find the Fourier series expression for this. Let me find the Fourier series expression for this. So how we can find? So here you no need to find the an value, right? So we need to find the bn value. So here let me find the bn value. So how we can find the bn value? So the bn equal to, so 2 by, because it contains quarter wave symmetry, we need to take the quarter period, that is pi by 2. So 2 by pi by 2, so 2 by pi by 2 which is equal to 4 by pi. So we need to integrate in between the 0 to pi by 2, that is enough. So 0 to pi by 2, 0 to pi by 2. So here the from 0 to pi by 2, its value is, magnitude is Vs. So it will be the Vs sin n omega t, sin n omega t d omega t. So sin n omega t d omega t. If I simplify this one, I will get the Fourier series expression. How I can simplify this one? So by simply integrating, we can get the expression. So here it will be the 4 by pi. So integration of sin n omega t equal to minus cos n omega t divided by n. So it will be the 4 Vs by n pi. So Vs is constant. So it will be the minus cos n omega t. So limits are 0 to pi by 2. 0 to pi by 2. So here if I substitute the lower limit and upper limit, so how I will get? So it will be the 4 Vs by n pi. So 4 Vs by n pi. So integration of sin omega t is minus cos n omega t. So that is minus cos n pi by 2. Minus cos n pi by 2. So minus of minus cos 0, which is the 1. So right, let me simplify further. So here we know that here even harmonics are 0. So that the n values are odd numbers. N values here is odd numbers. If I substitute n equal to 3, so odd number, if I substitute n equal to 3, 5 and so on, so I will get the, so cos n pi by 2 is 0 here. Cos n pi by 2 equal to 0. So I will get the expression as 4 Vs by n pi. 4 Vs by n pi. Bn value I got as 4 Vs by n pi. Now let me write the final expression. This expression is important. So this expression is important here. So which is equal to, so for a square waveform, so the function output voltage V0 of omega t equal to sigma n equal to 135 to infinity, because even harmonics are 0 because of quarter wave symmetry. So it is equal to 4 Vs by n pi into sin n omega t. Sin n omega t. So if you remember the expression, it is well and good. So otherwise you can, if you can derive, you can derive. So but no need to derive here. So if you can remember this expression, you can write the Fourier series expressions. So corresponding Fourier series expressions we will see further. So now let me find the next one. So for this waveform, I have said 3 waveforms you have to remember. So this is the second waveform here. So here, so for this waveform we need to find the Fourier series. For that we need to find whether it has the odd wave symmetry or so even symmetry. So if you observe here, so it contains, so it represents a odd waveform. So it is a odd symmetry. So that is f of minus t equal to minus f of t, or else, so you can see that it is symmetry over the origin. It is symmetry over the origin. So if you observe, it is symmetry over the origin. So it is symmetry over the origin, so that it contains odd symmetry. So and also it contains quarter wave symmetry. What is quarter wave symmetry? X of 90 minus theta equal to x of 90 plus theta. X of 270 minus theta equal to x of 270 plus theta. So let me verify these two conditions. So here 90 will come here, right? 90 will come here. See, if I go to the left side, right? If I go to the left side, it is x of 90 minus theta. If I go to the right side, it will be the x of 90 plus theta. So it contains both are same. So x of 90 minus theta equal to x of 90 plus theta. So it is satisfying the first condition. So in the quarter wave symmetry, it is satisfying the first condition. So and the second condition is x of 270 minus theta equal to x of 270 plus theta. So x of 270 minus theta equal to x of 270 plus theta. So it will be like this, right? So it contains quarter wave symmetry. So let me find the Fourier series expression for this. How I can find the Fourier series expression? So because it contains odd symmetry, so if it contains odd symmetry, the Bn value is not equal to 0, An equals 0. So that no need to find the An value. And so here A0 is also 0 because the positive half area equal to negative half area. So that if you find the average value, it is also 0. So let me find the Bn value. Let me find the Bn value. So Bn equal to, so 2 by 2 pi, the 2 by pi by 2, that is 4 by pi by 2. So 4 by pi. So we need to integrate in between the 0 to pi by 2. So 0 to pi by 2, so from here to here, so alpha to pi by 2, this point is alpha, this point is alpha. So from alpha to pi by 2, so we need to integrate alpha to pi by 2. So alpha to pi by 2, so it will be the Vs sine n omega t d omega t. So if I integrate this, it is a simple integration, so that because integration of sine n omega t is equal to minus cos n omega t divided by n. So which is equal to 4 Vs by n pi, right? 4 Vs by n pi. So integration of sine n omega t equal to minus cos n omega t, right? Minus cos n omega t. The lower limit and upper limits are here, it's alpha to pi by 2. So alpha to pi by 2. So right, so if I substitute in this, so I will get 4 Vs by n pi, 4 Vs by n pi. So the upper limit is minus cos pi by 2, so minus cos n pi by 2, so n pi by 2, so plus cos alpha. So as we've seen before, so in this, if you observe, so the even harmonics are 0 because of quarter wave symmetry, right? So that cos n pi by 2 will become 0. Cos n pi by 2 will become 0. So the Bn value here, it is 4 Vs by n pi, 4 Vs by n pi into cos n alpha. So here n is there, right? So cos n alpha. So we got the Bn value. So if you know the Bn value, you can write the Fourier series expression. So you can write the Fourier series expression. So let me write the Fourier series expression here. So it will be the V naught of omega t. For this waveform, so V naught of omega t equal to sigma n equal to 135 to infinity. So because even harmonics are 0 and Bn is 4 Vs by n pi, 4 Vs by n pi into cos n alpha into sine n omega t, sine n omega t. So if you remember this expression, or you can do, so it will be easy to derive also. So it is important, So our second waveform also done. So let me see the third waveform. So let me solve the third waveform. So we need to remember third waveform also. This is the third waveform. So before that, let me solve this one. So if you observe, it is symmetry over the y-axis. So it represents, it is like an even function. So even if you find the Bn value, you will get the 0 value. So here we need to find the average value. Before that, the positive cycle area is equal to negative A cycle area. Even if you find the average value, there you get the 0 value. But here, only the positive values are there. So we need to find the average value. So for this, V naught of omega t equal to A naught plus sigma n equal to 1 to infinity. So an cos n omega t. An cos n omega t. So how I can find the A naught? So it is simple average value. So we need to find the area divided by time period. So what about area? So from minus beta by 2, so the area will be the beta, right? So the length will be the beta, height is Vs. So it will be so A naught equal to area is beta into Vs, and we need to find the period from the minus pi to pi, so it will be the 2 pi. Beta into Vs divided by 2 pi. We got the A naught value. Let me find the An value here. So how I can find the An value? So An is, so let me find the An value. So An is, so what about An? So the An equal to, so here 2 by 2 pi, because we are taking for the period of the 2 pi here. So that's why, so I am keeping here 2 pi. So 0 to 2 pi. So 0 to minus beta by 2, it is 0. Minus beta by 2, it will be the Vs, right? So it will be the minus beta by 2 to beta by 2. So it will be the Vs. Vs into sine n omega t. Sorry, it will be the cos n omega t into d omega t. Cos n omega t into d omega t. So right, so it will be the cos n omega t into d omega t. So if I substitute this, integration of cos n omega t is the sin n omega t. If I substitute the lower limit and upper limit, I will get the 2 sin beta by 2. So here, so after solving this one, so I will get the 2 Vs by n pi into sin n beta by 2. N beta by 2. Now we got the expression for this if I substitute in this. So what is that expression? So that expression I will write here. For this waveform, so I am writing the expression here. So here V naught of omega t So V naught of omega t equal to, so V naught of omega t equal to beta into Vs by 2 pi, beta into Vs by 2 pi, right, plus sigma n equal to 1 to infinity, sigma n equal to 1 to infinity. So right, so here it will be the 2 Vs by n pi into sine n beta by 2, 2 Vs by n pi into sine n beta by 2 into cos n omega t, cos n omega t. So this is the expression we got for this waveform. So but we require to find the Fourier series for this waveform. So how we can find this? So So observe here. So if you observe these two waveforms, what is the difference between these two waveforms? So observe here. So if I can shift this waveform by the beta by 2, if I can push this waveform to the beta by 2, so this waveform will come, right? So this waveform will be left shifted by, this waveform will be, so if you observe this waveform will be, so left shifted or right shifted by the beta by 2, So because of right shift, the Cn value will not change, only the pi n value will change. So for this waveform, so I can write, let it be the V naught 1 of omega t. So V naught 1 of omega t equal to, so beta V by beta Vs by 2 pi into sigma n equal to 1 to infinity, so 2 Vs by n pi, so it will not change, 2 Vs by n pi, so into sine n beta by 2 into cos n omega t, so we have to keep the minus or plus. So if you observe here, so this waveform, we wrote the expression for this waveform, we need to find the expression for this waveform. So this waveform is leads this waveform is lag this waveform. So V naught 1 lags the V naught waveform by beta by 2. So that it will be the minus beta by 2. So if it is right shifted, we need to keep the minus sign. So now these three expressions are important. So let me keep all these three expressions at same pace so that you can understand. So you can understand. So now, so we have found the Fourier series expression for these three waveforms, right? So for these three waveforms, so we have found these expressions. What is the expression for this? V naught of omega t equal to sigma n equal to 135 to infinity 4 Vs by n pi into sine n omega t. So we have already determined, right? So same expression I'm copying here. So here V naught of omega t equal to sigma n equal to 135 to infinity 4 Vs by n pi into cos n alpha into sine n omega t, right? So we got this expression also. So and we need to write the expression for this, right? So what is the expression we got? So we got the expression as V naught of omega t equal to so beta Vs by 2 pi, right, plus beta Vs by 2 pi plus sigma n equal to 135 to infinity 1 to infinity. So it will be the 2 Vs by n pi into sine n beta by 2 into cos n omega t minus beta by 2. So if you remember these three expressions, so here no need of mathematical calculations also. At this stage, no need to strain. So if you remember these three expressions, that is sufficient so you can find the remaining expressions for all the cases. So let us see the remaining things. So forget about whatever be whether it is inverter voltage or something. So forget about this thing. First observe the waveform here. So this expression for this waveform we have derived or not? So we have derived. So for a square waveform we have derived the Fourier series expression, right? So let me write the Fourier series expression. So here V naught and this peak value is VDC. So let me write the expression. What is the expression here? So V naught of omega t equal to V naught of omega t equal to sigma n equal to 135 to infinity 4. So and this value is VDC, right? So 4 VDC by n pi into sine n omega t. So we got the expression, right? So we have already derived. So and this is the expression for the output voltage of the inverter for 180 degrees mode of conduction. So here, so it will be the single pulse PWM output. So we will see it in further lectures, but so observe here this expression we have derived already. So and this is the single pulse PWM output. So what is the expression here? So it is the V naught of omega t equal to, so what is the expression? You know the expression, right? You can write for this. So V naught of omega t equal to sigma n equal to 135 to infinity 4 VDC divided by n pi, 4 VDC divided by n pi into cos n alpha into sine n omega t. So now you got the expression for these two. So is this sufficient? We have different waveforms in the power electronics. So let us see the next waveform. So by looking this waveform, you may get complex. Maybe you may feel that it is a complex, but it is not at all complex. So you can find the Fourier series expression for this. By easily you can find the Fourier series expression. So how you can find the Fourier series expression for this, we will see here. So this is the output phase voltage of 3-phase voltage source inverter for 180 degrees mode of conduction. With these basics we know the basics. So that is 3 waveforms we have derived. From that I will take the 2 waveforms and I will derive the output voltage expression for this one. So how I can derive? So observe here. So let me represent with other color. If you observe this waveform, so this is the combination of 2 waveforms. So observe here, let me put this as a VAN1. So here, this peak value is, 1/3 of VDC. So it will be the 1/3 of VDC. So from here to here. So again, from here to here also I will draw the 1/3 of VDC. So again here also 1/3 of VDC. But so in this period from 60 degrees, that is pi by 3 to 2 pi by 3, the value of VAN is equal to 2 VDC by 3. That is, in that period we need to add additional VDC by 3. So let me add the VDC by 3 here, VAN 2. So let me add the VDC by 3. So this magnitude will be the VDC by 3. So this is the VDC by 3. So what happens here? Observe here. So from 0 to pi by 3, from 0 to 60 degrees, what is happening here? So VDC by 3 is there. From 60 to 120 degrees, what is happening here? So it is VDC by 3. Again here also VDC by 3. So we will get the same waveform. So here also same thing. VDC by 3. So and here also, so we will get the same thing. So it is a combination of 2 waveforms. If I add these 2 waveforms, I will get the output voltage. So we know these 2 waveforms or not? So we know these 2 waveforms and we have derived the Fourier series expressions also. So now let us find the Fourier series expression for this one. So how we can find? So observe here. So concentrate here. So it will be the pi by 3 and it is the instant is the 2 pi by 3. So let me write the Fourier series expression directly for this one. So VAN equal to VAN1 and VAN2. Summation of VAN1 and VAN2. So VAN2. So what is the expression for VAN1? So we'll get the expression as sigma n equal to 135 to infinity. So it will be the, so here the value is VDC by 3. So if it is VDC, we need to write the 4 VDC by n pi. If it is VDC by 3, we need to write the 4 VDC by 3 n pi. So let me write this 4 VDC by 3 n pi. So into, so for example, for this waveform, so we have determined for the alpha and pi minus alpha. But in place of alpha, we have the pi by 3 here. Simply replace the alpha with the pi by 3. So it will be the 4 VDC by n pi into cos n pi by 3. So if I take common in the common as 4 VDC by n pi, 3 n pi, so it will be the 1 plus cos n pi by 6 into sine n omega t. See how simple it is. See how simple it is. So if you know these two waveforms, directly we can write the expression for this. So further we can simplify this one. So how we can simplify, you can observe here. So we know that here even harmonics are negligible. Even harmonics are negligible. So that, and one more thing we need to see here. So here triplen harmonics also 0. How it will be 0, we'll see here. Triplen harmonics are 0. Triplen harmonics are 0. So for example, triplen harmonics are nothing but 3, 6 is even harmonics, that is already eliminated. So we have to go for 9th harmonic. So 3, 9, so and so on, we need to substitute here. So if I substitute the 3 in this, cos 3 pi by 6, what is the value? 3 pi cos 3 pi by 6 is nothing but cos pi by 2. So cos 3 pi by 6 is nothing but, so cos pi by 2. So what is the value of cos pi by 2? So cos 3 pi by 6 is nothing but, so it will be the cos pi by 2. So it will be the pi by 3, sorry, it will be the pi by 3. So it will be the pi by 3. So if you observe here, so this value is pi by 3. This value is pi by 3. So cos 3 pi by 3, so on 3 will get cancelled out, it will be the cos pi, 1 plus cos pi is equal to 0. Cos pi equal to minus 1, 1 plus cos pi equal to 0. For example, if I substitute the 9, so there also, so it will get the 0 value. So here, for the triplen harmonics, this total term will become the 0. This total term will become the 0. But for the remaining harmonics, how it will be? For example, if I substitute n equal to 1. So what happens? So if I substitute n equal to 1, 1 plus cos n pi by 3, right? Cos n pi by 3. So if I substitute n equal to 1, so it will be the cos pi by 3. So cos pi by 3 is nothing but cos 60, it will be the 0.5, so it will be the 1.5. Similarly, if I substitute remaining thing also, I will get the 1.5 here. So if I replace this one as 1.5, so here triplen harmonics are 0, so that we have to write for expression as n equal to 6k plus or minus 1. So where k equal to 0, 1, 2 and so on. So here, so it will be the 6k plus or minus 1 to infinity. So it will be this value is 1.5. So 1.5 into 4 equal to 6. 6 by 3 equal to 2. So it will be the 2 VDC by n pi. 2 VDC by n pi into sine n omega t. Sine n omega t. So this is the expression for the, so phase voltage in the 180 degrees mode of conduction. So here itself you are learning means, so you can answer, you can write direct expression when you are learning the inverters. So let me solve the next one. So here this waveform is, so 3-phase voltage source inverter operating in the 180 degrees conduction mode, line voltage waveform. So forget about whatever be the voltage waveform. So here you need to observe the nature of the waveform. So here what about the nature of the waveform? So if you observe here, if this waveform is, so this instant is pi by 3 and this is 120 degrees and this is 180, right? And this gap will be the, so what about this gap? 180 minus 120. So this gap will be the 60 degrees. So we need to convert this waveform into known form. So that is, in the 3 waveforms, it should be in the one nature. So I have to shift this waveform by so to get this waveform, so I have to shift this waveform by 30 degrees. So 30 degrees, if I shift this waveform by 30 degrees, what happens? So it will be the 30, right? So it will be the 30. So and here also this gap is also will becomes the 30. So again I am telling that, so here observe that I am shifting this waveform by 30 degrees towards right side. So if I push this waveform by 30 degrees towards right side, what happens? I will get this waveform. So we know the Fourier series expression for this waveform, right? So let me write this Fourier series for expression for this waveform. Let it be the VAB1. So let me write the expression for VAB1 first. So how it will be? So VAB1 equal to sigma n equal to 135 to infinity. So what happens? It will be the 4 VDC by n pi. So 4 VDC by n pi. So and it will be the, in place of alpha we have the 30 degrees. 30 degrees is nothing but pi by 6. So it will be the cos n pi by 6, cos n alpha, cos n pi by 6 into sine n omega t. So this is the expression for this waveform. So we have got this waveform. So we need to find the expression for this waveform. How we can find this? We can find this expression. So if you observe these two waveforms, this VAB leads the VAB1 by 30 degrees. This VAB leads the VAB1 by 30 degrees. So now I need to write the VAB. So for this VAB, sigma n equal to 135 to infinity, n equal to 135 to infinity 4 VDC by n pi, 4 VDC by n pi into cos n pi by 6. It will not change, Cn will not change. And what is the value will be changed? So we need to add the phase here. We need to add the phase here. Because this waveform leading this waveform, this VAB is leading VAB1, so we need to give here 30 degrees, that is pi by 6. So this is the expression for this waveform. This is the expression for this waveform. And so we can write the expression for this one or not, you can see. So this is the output voltage for 120 degrees mode. So forget about what about the thing. So here this magnitude is VDC by 2 and this magnitude is VDC. So we have derived for this one. So can we derive for this one? So we can derive for this one also. So VAN equal to, so here VAN equal to, so for this VAN equal to, so sigma n equal to 135 to infinity. So 135 to infinity. So here 4 VDC by n pi. In place of VDC, we have to replace with the VDC by 2. So we have to replace with the VDC by 2. So it will become the 2 VDC by n pi. 2 VDC by n pi into cos n pi by 6. It will not change, right? Cos n pi by 6 into sin n omega t plus pi by 6. So n omega t plus pi by 6. Understand this concept, it is very useful. So simply we have shift this waveform by 30 degrees to get the symmetry waveform into known form. We are changing into the known form. So let me solve the next waveform. So this is the waveform for the source current waveform for the single phase semiconductor. So how we can find this waveform? So for this waveform, so let it be the IS. For this waveform, we need to write the Fourier series expression. What we have to do? So here, if you observe here, so this waveform is not in unknown form. So our waveform is, so both the sides be from 0 to here and pi to here have the same space, same distance. But here 0 to alpha, it is ending at pi. We need to shift this waveform into known form. How we can shift? So this gap is alpha. To make the symmetry, what we have to do? This waveform should be shifted in this. So we have to pull this waveform to the alpha by 2. So let me pull this waveform to the alpha by 2. So here, this is the waveform, right? Let me pull this waveform into alpha by 2. So I have shifted this waveform. So now this is the known form. So it will be the alpha by 2. So it is the pi minus alpha by 2. So we know the expression for this, right? So let me write this as a IS1. First I will write for the IS1. After that I will write for the IS. So IS1 equal to sigma n equal to 135 to infinity. And this magnitude is I0, right? So it will be the 4 into I0 by n pi into cos. So what we have to write? So in place of alpha, we have the alpha by 2 here. So that we will write the cos n alpha by 2 into sin n omega t. So this is for IS1. So but we have to write for the IS. How we can write? So IS equal to sigma n equal to 135 to infinity. So 135 to infinity 4 I0 by n pi into cos n alpha by 2 into sin n omega t. So what is the angle we should add? We should add the angle or we should subtract the angle. You should understand. So if you observe these two waveforms, what is the difference between these two waveforms? So we have wrote the expression for this, but we need to find the expression for this. So if you observe, this waveform is lagging the IS1 by alpha by 2. So by alpha by 2. So because of lagging, we need to give the minus alpha by 2 here. Cos n omega t minus alpha by 2. So this is the expression for the source current of the semiconductor. So we'll solve the problems also regarding this one. So now let me solve the next waveform. So this is the waveform for the source current. This is the waveform for the source current for the fully controlled converter. So how we can control how we can give this waveform? So observe this waveform. So if you observe this waveform, alpha to pi plus alpha, what is the distance between the alpha to pi plus alpha? Pi plus alpha minus alpha. So this distance will be the pi. So this distance will be the pi. So from 2 pi plus alpha to pi plus alpha, what is the distance? And this distance also be pi. So like it is a square waveform, So we need to shift this waveform, towards left side. That is, we need to pull this waveform so to get the known form. So let me pull this waveform here. So I will pull this waveform to the alpha. So now what happens? So I got the square waveform. So if I pull this waveform to the alpha, if I pull this waveform towards left side, so I will get the square waveform. I know the expression for this. So what is the expression for this? So let me write the expression for IS1 again. So let me write the expression for IS1. So IS1 equal to, for the square waveform, what is the Fourier series expression? The Fourier series expression will be sigma n equal to 135 to infinity. So 4 I naught by n pi into sine n omega t. So this is the expression for IS1, but we need to find the IS. So what is the value will change? So if you observe these two waveforms, what is the difference here? This waveform IS lags the IS by alpha. So this waveform IS lagging the IS1 by alpha. So let me write the IS expression. So here it will be the sigma n equal to 135 to infinity. So 4 I naught by n pi. So into sine n omega t. So we need to keep plus sign or minus sign. So you should understand that. So this waveform is lagging. If it is lagging, we should keep the minus sign. So it will be the minus sign. So we have completed the source current for the fully controlled converter also. So forget about whether it is fully controlled or semi-converter, but we have obtained the Fourier series expression for this waveform. So let me find the next expression. So this is the DC to DC converter expression. So how we can draw this one? So here it will be the 0. We have already determined for this. So here beta is there. So here it will be the T. So now for this waveform we have already determined. What is the expression for this? For the beta. So V naught of omega t equal to. So beta V by beta into Vs. Here it will be the Vs. So beta into Vs divided by 2 pi. So plus sigma n equal to 1 to infinity. So 2 Vs by n pi, right? 2 Vs by n pi into sine n beta by 2 into cos n omega t minus beta by 2. So minus beta by 2, n omega t minus beta by 2. So now let us write this expression for this waveform. So here what is the difference between these two? So here beta should be replaced with the dt. Beta should be replaced with the d into t. So let take the t equal to 2 pi. So let me replace beta with the d into 2 pi. So if I replace the d into 2 pi with the beta, so I will get the output voltage expression for the DC to DC converter. So it will be the V naught of omega t. So which is equal to beta. In place of beta we need to replace with the d into 2 pi. D into 2 pi divided by 2 pi equal to d into Vs. So it will be the d into Vs plus sigma n equal to 1 to infinity 2 Vs by n pi into sine n beta divided by n into d into 2 pi divided by 2, which is the sine n into d into 2 pi. So which is the n into d into pi, n pi into d. So into cos n omega t minus beta by 2. So this is the expression for the output voltage expression for the DC to DC converter. Now we have got the output voltage expression for the DC to DC converter also. So now let us solve the next question. So here, so this is the output voltage of the bipolar sine PWM technique. So for this waveform, so we can derive the expression, but so in a simplified way, so I have derived the expression. In the detailed course we have discussed this, but here, so I am giving the generalized formula to remember this one. So here, This n represents number of notches per quarter cycle. So what is the meaning of this one? Number of notches per quarter cycle. So quarter cycle is nothing but pi by 2. So what is the meaning of notches here? So if you observe here, before pi by 2, we have two notches here. So we have named it as a alpha 1 and alpha 2. So this instant is alpha 1 and this instant is alpha 2. So for this waveform, there are two number of notches. So here we should replace this n with the 2 here. We should replace the n with the 2. So if I replace the n with the 2, I can write the expression for this. So we can write n number of notches. For example, here alpha 1, alpha 2, alpha 3 notches are there. We can write the expression for that also by using this generalized formula. How I can write? See here. So let it be the VAB. So VAB equal to 4Vs by n pi. So it will not change, right? 4Vs by n pi. So it will be the 4Vs by n pi, VABn. Let it be the nth harmonic component. So VABn equal to, so 4Vs by n pi, so into 1 plus 2 into, so minus 1 power i. So minus 1 power i is nothing but, so it will be the minus 1. So 1 minus, so this is the 1 minus, so 1 minus 2 cos alpha 1. So if I substitute i equal to 2, what happens if I substitute i equal to, so minus 1 power 2, so it will be the 1 plus 1. So it will be the, so plus 2 cos alpha 2. For example, if the waveform contains 3 number of notches, what will be the condition? So if the waveform contains 3 number of notches, alpha 1, alpha 2 and alpha 3. So what is the expression? For 3 notches, what is the expression? So you can write the expression for the 3 notches also. So let me write the expression for 3 notches. So for 3 notches, it will be the, so VABn, VAB1. So for example, if the waveform contains 3 number of notches, so I should replace this n value with the 3. So how I can replace? That is 4Vs by n pi, right? So 4Vs by n pi into 1 plus, so 2 into, that is 2 into minus 1 power 1. So it will be the minus 1 minus, so here it will be the 1 minus 2 cos alpha 1. So plus, so if I substitute 2, so it will be the cos n alpha 2. So it will become the, so it is cos n alpha 2. So here also n is there. So 2 cos n alpha 2. So minus, for example, if I substitute 3, I equal 3, what happens? Minus 1 power 3 equal to minus 1. So it will be the minus, so 2 cos n alpha 3. So if the number of notches, I can increase the number of notches of the waveform. So you can write the expression for any number of notches by using this formula. So this formula is important. So here where n is the number of notches per quarter cycle, So it is for the 2 notches, it is for the 3 notches. So let me see the other one. So it is a unipolar PWM output. This we will discuss in the inverters, but observe this output voltage waveform and how to write the Fourier series expression for this we will see here. So if you observe here, this is a generalized formula for this. So how I can write this expression? So if you observe here, how many notches are there? So where n is the number of notches for the quarter cycle. So quarter cycle is nothing but up to pi by 2. So how many number of notches are there? So alpha 1, so alpha 2 and alpha 3. 3 number of notches are there. So I should replace this n with 3. So I should write the expression, so which is equal to VAB equal to minus 4VDC by, so n pi, minus 4VDC by n pi. This is the nth harmonic component. So minus 4VDC by n pi into, so if I substitute 1 here, so what happens? Minus 1, so into cos n alpha 1, that is minus cos alpha 1. So if I substitute the I equal to 2, so I equal to 2, what happened? N equal to, so minus 1 power 2 is nothing but minus 1 square is 1. So it will be the plus cos alpha 2. So if I substitute the 3 in the place of n, what happens? So minus 1 power 3 is nothing but minus 1. So it will be the minus cos alpha 3. So minus cos alpha 3. So this is all about deriving the Fourier series expressions, and we have derived the Fourier series expressions for the different waveforms by using simply 3 waveforms. So in the next session, so let us solve the problems regarding the Fourier series.